Good evening, and welcome to what I think is going to be a very interesting, exciting start to the events of the next 24 hours. So I am Tom Prince, Bowen Professor of Physics at Caltech and Director of the WM Keck Institute for Space Studies. The program this evening is an activity of the Keck Institute, and we believe that this is the largest audience we've ever had for a Keck event. I see that we've just past 1,200 participants, and it's still climbing. The background that you can see behind me is a virtual rendition of our home, the WM Keck, at the WM Keck Center on the Caltech campus. You can see the historic Tullenbacher House on the right and our modern conference center on our left. We are very, very grateful to the WM Keck Foundation and more recently to the Caltech Space Innovation Council for their generous support of our institute. We just couldn't be doing the things that we do without them. So you might ask, what is the Keck Institute for Space Studies? In essence, we are a think tank for new ideas about space exploration. We carry out our work jointly with the Caltech Jet Propulsion Laboratory, and we endeavor to bring together the best scientists and engineers from the US and around the world to participate in our brainstorming and our studies. Our goal is simple, to come up with new concepts that have the potential to significantly impact the future of space exploration. We undertake studies in planetary science, earth science, astronomy and astrophysics, and space engineering. Since our start in 2008, we have carried out over 60 different programs or studies. And we have been rated among the better US science and technology think tanks each year for the last 10 years. Turning to tonight's program, if you have attended other Caltech webinars, tonight will be a little bit different because after all, we are the Keck Institute and we tend to do things a little bit different. Let me explain. One of our goals is to develop the next generation of space scientists and engineers. Among the activities of the Keck Institute is what we call the Affiliates Program. They're a fabulous group of Caltech graduate students and postdocs interested in science and engineering. So the affiliates come together for pizza about once a month to hear a talk by a prominent space scientist or engineer. Tonight is just such a get-together. The affiliates will be having pizza, really. They really will be having pizza right after tonight's talk. Using a separate Zoom link, and they'll be discussing tonight's talk and tomorrow's lunch. I'd like to now call on one of the leads of the affiliates group, Mike O'Connell, a Caltech graduate student in aerospace engineering. Since this is an affiliates event, Mike will be introducing the speaker and directing the question and answer period afterwards. So now I have the pleasure of introducing Mike, who will be your host for the rest of the evening. Thanks for joining the Keck Institute affiliates for this talk, and enjoy the rest of the evening. I'm going to enjoy it myself. Okay, Mike, over to you.
Thank you, Tom, and thank you everyone for joining for our first virtual KISS webinar. Tonight we are very excited to hear from Dr. Katie Stack-Morgan to discuss seeking signs of ancient life in Jezero. Dr. Stack-Morgan is a research scientist at the Jet Propulsion Laboratory. She is the Deputy Project Scientist for the upcoming Mars 2020 Perseverance rover, and she is a participating scientist on the Mars Science Laboratory Curiosity rover mission. Dr. Stack-Morgan graduated with a BA in Geology and Astronomy from Williams College, and she earned her MS and PhD in Geology from Caltech. She's earned a number of impressive awards, including the Forbes 30 Under 30, Mars Science Laboratory JPL Voyager Award. She was a finalist for the MIT Technology Review Innovators Under 35, and she has earned several other honors. Dr. Stack-Morgan is interested in researching Martian sedimentology, stratigraphy, and orbital geologic mapping. She studies the Martian sedimentary rock record using orbital and rover image data to understand the evolution of ancient surface processes on Mars. So, without further ado, please help me welcome Dr. Stack-Morgan.
Thank you, Michael, for that introduction, and also to the Keck Institute of Space Studies for inviting me here today to talk with you all. I remember when I was a graduate student at Caltech that I attended several KISS events, and so it's very exciting to be here today as a speaker talking with all of you. It feels like I've come full circle here. Today, I'm going to talk with you about the Perseverance rover mission and our goal to seek signs of ancient life in Jezero crater. And of course, we are on the launch pad now and scheduled for launch in just under 12 hours, which is just mind-boggling and incredible to me that we are where we are right now. We've spent the past couple of months, a team of engineers down at the Kennedy Space Flight Center, getting the rover ready for its journey to Mars. And you can see on the left here, as we packaged the different components of the mission together, and then enclosed the capsule in the nose cone. And here we are ready to head to Mars tomorrow at 4:50 a.m. East or 7:50 a.m. Eastern time, 4:50 a.m. Pacific time. So very early in the morning for us here on the West Coast. So I'll tell you a little bit today about what the science objectives of Mars 2020 and the Perseverance rover are, and what we're hoping to find in Jezero crater, and our contributions to the Mars sample return campaign that we are really kicking off with this mission. And so here's our mission timeline. Of course, here we are getting ready for launch. We will, once we launch, we'll cruise to Mars for the next several months and landing on February 18th, 2021. And then we will begin our surface operations on the surface of Mars for a prime mission of 1 Mars year, or about 2 Earth years. And so we are ready to go and excited to send Perseverance on its way tomorrow morning. And so I'll start here with the Mars Exploration Family Portrait. And these are the successful missions that we have sent to Mars, and Perseverance of course, is excited to join this very distinguished group of robotic explorers. But you could ask, why Mars, why now, and why this mission? And so I hope today to answer those questions and explain to you why we are so excited about this mission and why this mission is such an important addition and the next step in our exploration of the solar system. Many of you are probably familiar with the Mars Exploration Program goals, being the study of life on other planets, particularly Mars, understanding the climate, learning more about the geology, and preparing for human exploration. And the threads that hold all of these together are very familiar to us now. First, we had the search for water on Mars, and that was really the objective of the Mars Exploration Rover, Spirit and Opportunity. And then that led to the search for habitable zones and habitability on the planet Mars, and Curiosity exploring Gale crater has really knocked it out of the park with that one. But still unresolved for us is whether there was ever life on Mars in the past. And that's really where Perseverance seeks to make its biggest contribution to our understanding of Mars and its potential as a place to host ancient life. And so we're optimistic about Mars having evidence of ancient life, not because of what it looks like today, which is a relatively dry, barren landscape that we think of as being uninhabitable by life as we know it. But Mars, 3.5 to 4 billion years ago, likely looked a lot different. And we know from abundant sources of data that there was flowing water on the surface, and we have interesting hydrated minerals that tell us that, and the rovers and landers have discovered ancient habitable environments. And so everything points to the fact that Mars was once a habitable planet and could have supported life. But when we think about the search for life, I think the first place we start, of course, is our own rock record. The oldest accepted evidence for life on Earth is about 3.5 to 3.6 billion years old. But given the fact that we have it preserved in rocks of those age, it's very likely that life started before then. And some of our best examples of ancient life on Earth come in the form of these fossilized microbial mats, something that we call stromatolites. And these are 2 examples from some of those most ancient rocks from Australia. But the thing about Earth is that because of things like plate tectonics and all the water we have on the planet and our climate, we don't have a lot of really ancient crust exposed on Earth. And so it's even a marvel that we see the evidence for ancient life that we do. And this map shows the location of those really ancient places here on Earth. And you can see that they're few and far between. But the exciting thing about Mars is that about 50% of Mars's surface is older than 3.6 billion years old. So Mars provides a window into a period of solar system history that our own Earth doesn't. And this period of time on Earth is when life was arising. And so if life arose on Mars, we have an opportunity to explore the Martian rock record to see the development of life in the solar system if it were there on Mars by studying ancient Mars rocks. And so our focus in terms of understanding life elsewhere in the solar system, I think is really, really well placed looking at the ancient Mars rock record. And so, of course, life is one of the big outstanding questions that we are after on Mars. Was life present on Mars? And what was the prebiotic chemistry like for a planet like Mars that we think was once habitable? And so that's something that we're really interested in learning more about and gaining more insights on. Some of the other areas of Mars science that are still really open questions and that are high priority questions for us to resolve are first chronology. Here on Earth, we have a very well-developed, well-defined geologic timescale, and that's thanks to our ability to absolute age date rocks here on Earth and the development of techniques that can do that. But on Mars, we are reliant on a calibrated crater chronology based off of lunar samples and lunar cratering rates. And so folks in the Mars community believe crater chronology on Mars to different extents. But what we're really interested in doing for Mars is putting in a geologic time series with actual absolute age dates, the timing of some of the major events we know happened in Mars history, when the volcanism occurred, when there was abundant water on the surface, when the valley networks formed, and when did Mars start to transition from a habitable to an uninhabitable planet? So those are all really open questions. And then I think also we have unresolved the evolution of Mars as a system. How did the surface, the atmosphere and the subsurface interact with each other? And we've made major advances in that area on Earth thanks to isotopic studies, as we've been able to characterize elemental reservoirs here on our own planet. And a good example of that is the carbon cycle. And so we're looking on Mars to connect the different parts of the Martian system. And we've really struggled. I think we haven't been able to do that yet with the robotic missions that we've sent to Mars. And so with these outstanding questions, this really motivated the idea in the last Planetary Science Decadal Survey, which is something that NASA commissions every decade to think about and present what the vision is for planetary exploration. And so in the last one that occurred in 2013, there was a very strong statement from the Mars community that the Mars sample return and a sample return mission is the logical next step in Mars exploration, and that the only way we're going to address some of the important questions I just talked about is with the analysis of returned samples. And so the last decadal survey ranked a Mars exploration and sample collecting rover as the highest priority flagship mission for the next decade. And in response to that, we had the development of the Mars 2020 mission. And you could say, well, we have Martian samples already. Why is Mars sample return so important? And it is true that we have over 250 plus confirmed Martian meteorites now that have fortuitously found their way to Earth. But as it turns out, these rocks aren't quite as diverse as we might like them to be. They're all igneous in origin, and they may have come from a very small number of impact events. They also record very little of the different surface processes that we know occurred on Mars, including those that are perhaps most conducive to preserving evidence of life. And these rocks completely lack geologic context, which I hope to show you is a really important part about how you approach and try to answer the question about whether life was present on Mars. And so Mars science missions and Mars sample return really seeks to fill in these major gaps in our scientific knowledge. So following on that, we have the development and proposal of Mars 2020, which came after Curiosity's astoundingly successful landing on Mars and its very successful first several years. So around the kind of 2013, 2014 timeframe, Mars 2020 as a mission really started to come into focus. And so the mission has four main goals. The first is to study the geology and habitability of its landing site. Objective B, I think, is where we really start to take a step forward for Mars exploration and specifically seek the signs of ancient life on Mars. And that's towards the eye, in the direction of putting together a sample cache, which is Objective C, that is scientifically compelling and returnable to Earth. So those are kind of the main scientific objectives. And we also have an objective, as previous rovers have had, to make advances in our preparation for sending humans to Mars. And I'll talk a little bit about how we are accomplishing that objective. And so I'll tell you a little bit about Perseverance, and this talk is mostly about the science of the mission, but I'll start with a couple of teasers about the exciting and cool new capabilities that this rover has compared to previous rovers. But Perseverance is built on Curiosity heritage. So when you put the rovers side by side, they look very similar, same chassis. And that was a cost-saving measure, and that allowed Mars 2020 and the Perseverance mission to focus on some of the exciting new advances that we wanted to incorporate into this mission. That particularly was relevant for accomplishing the science objectives that Perseverance has. And so we have a new and updated science payload and sampling capabilities that I'll talk a bit about in a couple of slides. And so this is the kind of introduction. And so I'm on the Curiosity rover team, and so I think of Perseverance as standing on the shoulders of giants there, with Curiosity just being such a fantastic mission and really setting the stage for Perseverance to do its thing on Mars. Okay, so I'll talk a little bit about the exciting things that we have in the engineering realm for Perseverance. And the first is a new landing technique. Previous rover missions have been largely at the whim of winds on Mars, as the rover and its heat shield and back shell are descending through the Martian atmosphere. But thanks to a new technology called terrain relative navigation, we can now, and the addition of a new computer that has greater computing power, we've uploaded a map of the hazards at the landing site that Perseverance is headed to. And as we're descending through the atmosphere, we take an image of the surface of Mars, and we do a comparison between our hazard map and what we're seeing through the eyes of the mission. And we can avoid hazards. And that's allowed us to consider landing sites that were never on the table before. And with previous landing capabilities, for example, those on Spirit and Opportunity or Curiosity, we wouldn't have been able to go to Jezero. So it's thanks to this capability that we are going to the site that we are going to. So that's very exciting for us. We also have improved the mobility system. One of the early unexpected challenges on Curiosity was degradation of the wheels as we roved over the rocky terrain, and the wheels didn't respond as we had expected. And I think it was 300 or so sols in, we noticed these gashes in the wheels that started to form. And as soon as that happened, we started to see the wheels on Curiosity as a consumable. And we've been very careful to try to mitigate damage to the wheels over time, and we've been successful in doing that. But on Perseverance, we didn't want to have to worry about that. So we've made some updates to the aluminum wheels. And also, one of the fun things that Curiosity's wheels had, they have JPL in Morse code cut into the wheels. And that was actually to help assist in auto navigation and helping the rover to see its tracks. But because we have updated engineering cameras, we don't need to do things like that for Perseverance. And our engineering cameras can see the very subtle tracks left behind the treads that you see there on the right. So that's one advance we have in the mobility system. And I'll also mention the sampling and caching system on Perseverance. It is a brand new system and the most complex robotic system we've ever sent beyond Earth. This is an incredibly complex system. And this rover has not only one arm, but two, and it has a sample handling arm in the body of the rover that's responsible for manipulating the sample tubes inside of the rover as we collect samples. And that arm moves the samples to different stations as we characterize them and seal them within the body of the rover. So this is a very exciting new capability that we have in preparation for Mars sample return. We also have the ability to be very flexible in how we think about the samples and how we deposit them on the surface of Mars and prepare for what we hope is the next leg of Mars sample return. And so we have the ability to either hold on to the samples with Perseverance and they can stay inside of the rover, but we also have this ability to depot them, so to place them on the surface of Mars as it is strategically valuable to do so. And so that's something that we'll be thinking about as we rover on the surface and thinking about the strategy involved with getting those samples on the ground in the right place and in the right place for the next follow-on missions to pick them up. So that's a capability that we have with this rover as well. Okay, so I'll talk a little bit about the science payload on Mars 2020 Perseverance rover, which is the other update compared to Curiosity. And so some of these instruments are familiar to us in that they have heritage on Curiosity, particularly Mastcam-Z, Mastcam, without the Z, without the zoom capability, is flying on Curiosity and taking images of the Martian surface now. And SuperCam's precursor was ChemCam on MSL. And Meta as well, our weather station, had its origins as REMS on MSL. But we also have brand new instruments on this rover as well. So both of the instruments on the end of the rover's arm, Sherlock and Pixel, are brand new, as well as RIMFAX, the first time we're going to do subsurface radar on Mars. And we have MOXIE, and I'll talk more about MOXIE and what that does. So I'll step through each of the instruments very briefly to give you an overview of what they're capable of. So I'll start with the context instruments, the instruments that really, whose function is really to give us the geologic context of the landing site and help inform more detailed analysis with some of the instruments on the rover's arm and get us focused towards a sampling decision. And so here we have RIMFAX, a ground penetrating radar designed to produce high resolution stratigraphic information about the subsurface. And we expect to be able to see down to a depth of up to 20 meters. So we hope to be able to resolve the stratigraphy of the subsurface that will help us better understand the relative age relationships of our landing site. As I mentioned, Mastcam-Z, so there's a mass-mounted geologic stereoscopic and multispectral camera system equipped with a zoom function that actually got descoped from the cameras that were planned for Curiosity. So we brought that capability back for this rover and are excited to be able to zoom both of our eyes and see what the Martian surface has to tell us with the rover's eyes. We have SuperCam. This is a remote sensing instrument that uses optical measurements and laser spectroscopy to determine fine-scale mineralogy, chemistry, and atomic and molecular composition of samples. And this truly is a super instrument. ChemCam on MSL does LIBS and takes images with its remote micro imager. SuperCam does LIBS, near infrared spectroscopy and Raman spectroscopy, and the camera is a color camera. So it really truly is super and a super update to the ChemCam instrument that's flown on Curiosity. And then we get to the new instruments, and these are the ones in the rover's arm. And so we have Pixel, the planetary instrument for X-ray lithochemistry. And so this instrument uses an X-ray fluorescence spectrometer and an imager with really high resolution to determine sub-millimeter scale elemental composition. And this is where I get really excited as a scientist, because for the very first time, we are able to spatially resolve elemental chemistry with a rover on Mars. Previous rovers have focused primarily on obtaining bulk analyses. But with this capability, we can actually match elemental chemistry, the distribution of elemental chemistry in the rocks with fine textures. And that's the start of how we start to build a case for a potential biosignature on Mars. Also contributing to this is the Sherlock instrument, which is a deep UV resonance Raman and fluorescence spectrometer that uses a less than 100 micron spot size to determine fine scale mineralogy and detect organic compounds. So this is also a mapping instrument capable of spatially resolving the distribution of minerals and organics in the rocks we see. So we add that working together with Pixel, and we now have spatially resolved elemental chemistry, mineralogy, and organics. And that can be really powerful. If you think of the example of the stromatolite, what we might expect to see with these instruments if we were looking at an Earth stromatolite is perhaps concentrations of organic molecules alternating with systematic mineral concentrations that might start to tell us that life could have been involved in the formation of that particular rock. And that's how you start to build a case for biosignature. And for the very first time, we can do that on Mars with a robotic explorer. Part of the Sherlock instrument is the Watson camera, which is heritage on Curiosity's Mars hand lens imager, the MOLLE camera. And that's what's going to provide us that fine scale texture on which we can overlay the maps from Sherlock and Pixel. So that's I think probably for me the most exciting new capability, science capability that this rover has that I think makes this rover uniquely well suited to search for biosignatures on Mars and really make advances in situ in that area, as well as helping inform sample decisions. And we've all come to know and love the selfies that Molly takes on Curiosity. And so because we have Watson, we'll also be able to do this. So we will be returning selfies from a new place on Mars and providing just what are some of the most spectacular images that come to us from Mars. And so now I'll move into the two instruments that are related to our fourth objective, which is human exploration. And so we have the META instrument, which is a suite of environmental sensors that measure and monitor the present day atmosphere of Mars and measure things like wind speed, pressure, temperature, and relative humidity, and can give us a weather report every day. And this is an example from InSight. And so in order for us to better understand how humans could work and live on Mars safely in the future, it'd be really important for us to know this kind of information so that astronauts can be as prepared as possible to carry out their work on the surface. And so this is contributing, the results of this instrument will contribute towards that understanding. And then we have MOXIE, which is a technology demonstration. And the purpose of this instrument is to take CO2 from the Martian atmosphere, convert it into oxygen by basically running a fuel cell in reverse. And the idea behind MOXIE is that when scaled up, could be the kind of instrument that produces oxygen that could be used for propellant to get astronauts on Mars back to Earth. Mass is money when you're sending a spacecraft, and if you have to bring all the fuel with you to get you back home, that's the dollar signs are going to go up on that. So this is one way that we can think about making some of those resources in situ on Mars to get us back home. Also, oxygen, of course, could be useful for keeping the HABs going and providing a habitable environment for future Mars astronauts. So that's the payload. And as I teased before, Perseverance represents a real evolution in the capabilities, the observational capabilities of Mars rovers. And so we started in the mid-90s with Sojourner, which was in itself a technology demonstration on the Pathfinder mission. And that very small rover, very small but capable, could do bulk geochemistry, but didn't sample at all. And it roved around a very short distance, making observations of those very large boulders that you see there at its landing site. Then we move on to the Mars exploration rovers with Spirit and Opportunity. They were capable of abrading the rock surface with an abrader to clear away some of the coatings and dust that are present on many Martian rocks. And we're able to do bulk geochemistry. That's true as well of Curiosity that could do bulk geochemistry, but we added in mineralogy and the ability to detect organics. And those were the two instruments that really made Curiosity a laboratory. And so, but with Curiosity, we do powder drilling. So when we drill, we create powder, basically destroying any kind of textures that might be present in the rocks. And that's not ideal for Mars sample return, because one of the ways you make the case for biosignatures is having those fine scale textures and studying those and looking for that. And so for Perseverance, we needed to do something different than the way MSL approached its sampling. And I think in each one of these cases, for these missions, sampling really supported exploration. But what we say for Perseverance is that we have exploration in support of sampling, because sampling is such an important fundamental core goal of this mission. The exploration that we do with our science instruments is really in service to making decisions about which sample should go in our sample cache for Mars sample return. And so here we will use our spatially resolved geochemistry, mineralogy, and organics to help us make decisions about which samples are the most compelling and which may have the best chance of containing biosignatures. And so here's an example of the kind of thing. And I mentioned the microbial mat before. And so here we have one of those Australian stromatolites. And on the right, you can see the kinds of maps that we can get out of a pixel-like and a Sherlock-like instrument that shows those concentrations of elements as well as organic carbon. And when you start to match up each of these different data sets together, you can start to ask questions about, is this a kind of pattern that we would expect from an abiotic process, or is this a texture or a pattern that required life to form? And so that's how we'll make the case for potential biosignatures on Mars with Perseverance instruments and observations in situ. And so what our exploration model is to take the geologic context data that we get from instruments like MassCAMZ and RIMFAX, as well as META, and combine this data at a range of spatial scales that will really help us decide which samples are the most promising for answering that question and seeking the signs of ancient life. And so we'll develop a geologic model and an understanding of the depositional environment and the surface processes that led to the deposition of those rocks to maximize our opportunity of selecting samples that will tell us more about Mars as a planetary system and to help us determine whether life was once supported on Mars in Jezero crater. Okay, so speaking of Jezero, I'll now take a turn and talk about our landing site and why we're so excited that Perseverance is headed to Jezero crater. And so the landing site selection for Mars 2020 and for Perseverance was a 5-year-long community effort that culminated in NASA headquarters selection of Jezero as the landing site for Perseverance in the fall of 2018. And what you see here is the final 3 locations, and there's actually 4 in that there were 2 potential ellipses in the northeast Syrtis area that we were considering. And I think each one of these landing sites certainly had its advocates in the Mars community, and each were exciting for their own unique reasons. We had Jezero, which is the site of an ancient delta and lake with very diverse and unique mineralogy for a lake delta site on Mars. But we think of Jezero as a surface site in a way, in that the ingredients that make it most compelling from an astrobiological perspective were present at the surface. So we had standing bodies of water at the surface of Mars. But there were folks in the community who thought that maybe looking in the subsurface might give us a better chance of finding signs of ancient life on Mars, especially with some of the unknowns about how habitable or uninhabitable the surface of Mars was in the past, that maybe life might have found a niche underground and could have really thrived there. So there was a lot of interest in northeast Syrtis, which is amongst some of the most ancient crust on Mars, and was thought to be impacted by numerous aqueous events and activity over the course of its history. The ancient crust exposed in northeast Syrtis also exposes some really exciting impact deposits from one of the largest impact basins on Mars. And so there was the potential there to learn about some of the most catastrophic but important processes that occurred in Mars' past by looking at rocks like that. And then finally, there was Columbia Hills, which may be familiar to you as the site of the Spirit rover, and Spirit roved there at the Columbia Hills and eventually ended its mission there. But there was a very exciting and compelling discovery of a potential biosignature at the Columbia Hills, and it was in the form of what was interpreted to be a stromatolite and silica-rich stromatolites. And so that was put out there as a really compelling target for Mars 2020, because it's the only place on Mars where an interpretation has been kind of accepted that we had a possible biosignature. But I think in general, the Mars community was really excited about exploring a new site on Mars. And so I think Columbia Hills certainly had its pros and cons when it came to a landing site. But ultimately, NASA headquarters made the selection of Jezero, and I think that was a decision that made a lot of sense, because as compelling as these other sites are, and northeast Syrtis with its great potential for sheltering life in the subsurface, we have, I think, the best understanding of how to search for life in a place like Jezero, in a lake delta site. And we can really hit the ground running with Perseverance, and we know exactly where to send the rover in this delta environment, and I'll talk about that, to go to the places where we think we have the best chance of finding life. I think it's a little bit harder to search for life in ancient impact or volcanic rocks, and the exploration model there wasn't quite as sharp. And so given the ambitious goals of the mission and the ambitious timeline that we're working on, Jezero really, I think, made sense as the landing site for Perseverance. So I'll talk a little bit more about that and the context and the geologic context of Jezero. And so here we have Jezero crater, which is perched on the inner rim of the inner western rim of the Isidis impact basin, which is one of the largest impact basins, and there's a small family of these really giant impact basins on Mars. This is amongst the youngest one at about 3.9 billion years. And so based on the relationship, we think that Jezero was younger than Isidis, so somewhere around very likely 3.8 to 3.9 billion years itself. This is also a very interesting area of Mars. We have the Nili Fosse, where a lot of very spectacular mineral discoveries have been made. And there are some similarities and correlations between that area and the minerals that we see detectable in Jezero crater. And this part of Mars is kind of bookended by the Isidis Impact Basin on the old end and Syrtis Major volcanic activity on the younger end, and that's between 3.5 to 3.8 billion years ago. So this part of Mars and Jezero crater and its and things that happen in Jezero are kind of within this 500 million year range, bookended by these two very major, and I'll mention potentially datable events. And that, I think, was very exciting to us for a Mars sample return perspective in terms of understanding and calibrating and giving absolute age dates to some of the major surface processes and things that we know impacted the Martian surface. So this is the context of Jezero, and we'll zoom in here to Jezero crater itself. And one of the reasons why Jezero crater stood out amongst its peers, landing site peers, because there are a lot of craters on Mars, of course, and there are a lot of craters that we think might once have hosted lakes. But there are very few craters that have what Jezero has. And one of the reasons we know that it's a slam dunk that there was an ancient lake in Jezero crater is because there is a river valley that flows in, and that's labeled here as the inlet valley. And a lot of craters have that. But there's also an outlet valley. So we know in order for an outlet valley to form that Jezero crater basically filled up like a bathtub and got to a point where it then overflowed and water flowed out of the crater. And so that's pretty solid evidence that there was a standing body of water in Jezero, and that is exciting from an astrobiological perspective because it indicates or suggests that there was a standing body of water in Jezero for a geologically significant amount of time. And of course, we don't know exactly what that time is now based only on our orbital data, but that's something that we could seek to answer with samples that come back from Jezero. And of course, there's the Jezero Delta. Deltas form when rivers enter an open body of water. But a form like that doesn't necessarily have to be a delta. We could have an alluvial fan like you're all probably familiar with from Death Valley, and those are very kind of intermittent events that happen. But when you combine the evidence of the outlet valley plus the delta, that's where we really start to feel quite confident that there was an ancient lake present in Jezero, and that this is one of the best sites where you don't have to poke around to find that out. You can see that already with the orbital data. And that's one distinction between Jezero crater and Gale crater, where Curiosity is exploring. And the real draw with Gale crater what is the 5 kilometer thick mound of sedimentary deposits that gives you the chance to observe just a big chunk of Mars time and to step through that layer by layer with the rover. And we've also interpreted a delta to be present in Gale crater, but we had to really work for that interpretation. It wasn't obvious from orbit, it wasn't obvious in the images, and we had to piece that together based on observations from the rover. And I'll say that all of that takes time, and we feel confident in that interpretation as well, but you spend time trying to put that story together. And given our objective of putting together a sample cache that could be picked up by a follow-on mission as early as kind of the 2028 timeframe, we don't want to spend a lot of time trying to understand where are we, what are these rocks. So Jezero is very appealing in that way, in that we know what we have here and we know where the rover should go to put together a compelling, diverse sample cache that has evidence for potential life on Mars. Okay, so the other interesting thing about Jezero and how it distinguishes itself from other deltas or ancient crater lake basins on Mars is its interesting mineralogy. And so here you'll see a zoom in of the delta, but the spectroscopy data that we obtained from orbit, and this is from the CRISM instrument on the Mars Reconnaissance Orbiter, shows some very interesting mineralogy, in particular carbonates along the inner margin of what would have been ancient Lake Jezero. And I'll show you a close-up of that in a couple slides, but the presence of carbonates in the shallow margins of a lake is a very compelling astrobiology target, because that's exactly where you might expect carbonates to form and a habitable environment to be formed. And that's exactly where you might go to look for something like a fossilized microbial mat. Life on Earth loves carbonates, and carbonates love to preserve evidence of life. And so the carbonates in Jezero are one of the really compelling astrobiology targets that we have to look forward to with the Perseverance mission. The other appealing thing about a sedimentary system like the delta in Jezero is the fact that Jezero has a very extensive watershed. So the area over which we think rivers flowed and carried sediment and rocks and sand into Jezero. And so even though we're only able to go to a single location on Mars, with Perseverance, of course, we have the opportunity to, in a way, sample a much larger, wider area. And of course, the sediment that comes into Jezero doesn't have the context you would necessarily, the in situ context of the rocks being where they were formed. But this gives us an opportunity to at least sample the diversity of rocks coming from some of these most ancient terrains on Mars. And so that's a really compelling opportunity that we have here that not all sites would give you the opportunity to do. So that's a very exciting thing about this location as well. And so I'll take us through a quick tour of some of the geologic units in Jezero that the rover, we hope the rover will be roving over in just a couple of months. And so here we have Jezero, and the first up is what we call the mafic crater floor. And I talked earlier about our desire to do absolute age dating on Mars. And so one of the things that was a hot topic during landing site selection was whether the different sites that were under consideration had potential volcanic units, because volcanic rocks are really well suited and great for absolute age dating. And so the best candidate we have for that in Jezero crater is this mafic crater floor, which is a very heavily cratered resistant unit. And it looks very similar to what has been interpreted as lava flows in other craters. It's not for sure that this is a lava flow, but it's probably the best candidate that we have for something that could be volcanic. And based on what we know, this is what it looks like. Zoom in here, and each one of these little shadows, I don't know if you can see my mouse, but each one of these shadows and blocks does represent a large block on the surface. And so the engineers don't want us to really land on this unit because it's not particularly safe terrain, but we might expect it to look something like this. And this is just an example from Death Valley showing these big chunks of basalt. And so if this is indeed a volcanic unit, we would certainly be interested in sampling one of these blocks if we can to give an absolute age date to units and units deposited within Jezero. Then we'll move out from the center of the crater to the olivine and carbonate bearing floor unit. So this is a unit exposed within the floor of the crater that has olivine and carbonate minerals exposed in it. And so we're unclear whether this unit is part of a more regional unit that shows olivine signatures going beyond the crater, or it could be a unit that was deposited in ancient Lake Jezero and filled the basin. And so because of the presence of carbonates, this is another unit of high astrobiological potential and interest to us. And so we'll certainly be exploring that as well. There's also been an interpretation that this could also be a volcanic unit. And so we'll be thinking about that potential and possibility as well as we explore it with Perseverance. And so this unit doesn't retain craters the same way that the mafic crater floor does. And so we have an idea that this is probably a softer material. And so here I show a very soft material, which is a volcanic ash. So it might not look exactly like that, but if this was indeed a volcanic ash, that would again be incredibly exciting for the potential to get an absolute age date from a unit that is present in Jezero. And if it is a regionally extensive unit, that gives us the potential to put an absolute age date even beyond the confines of Jezero and put into absolute age order some of the events that occurred outside of Jezero as well. Okay, so then when we have the delta, which is one of the main draws for Jezero. And so here in the delta, we have diverse river deposits, fine-grained rocks at the base of the delta with high organic preservation potential and of great astrobiological interest. And we know a lot about how to explore deltas and how to look for organics in deltas, thanks to the oil and gas industry here on Earth. That's exactly what they do. And so they study sedimentary systems to find organic matter. So we can actually farm that literature and all of that, about 100, 150 years of knowledge studying these types of systems to tell us exactly where to go to find evidence of ancient life and concentrations of organic matter. So our focus will likely be on the layers that were deposited the furthest out into the basin, where things tend to be very calm and where you have concentrations of organic matter as that organic matter settles through the water column and is deposited on the floor of the lake. So that'll certainly be a focus. But we're also interested in the diverse river deposits at the upper surface of the delta, with our eye towards that diversity, and thinking about the diversity of class. And if the other units within Jezero are not volcanic, our best chance of getting a datable unit may actually be in one of those boulders preserved in the river deposits of the delta. So we'll be keeping our eye on that as well. And this is an example of what that delta might have looked like at some point in the past. The Jezero Delta has just beautiful sedimentological structures, and I'm a sedimentologist, a Martian sedimentologist, and so these are the kind of images that are just mind-boggling, that you can trace out point bar deposits, and so these are classic deposits that you would see in terrestrial rivers. And those distal deposits out into the basin where we think we might have concentrations of organic matter, we see those as well in Jezero. And so this is just a sedimentologist's delight, and I can't wait to explore it. Okay, and we also have remnant deposits. And so these are interesting deposits in that they give us a hint that the Jezero Delta is more than it appears today, and that it very likely was more extensive at one point in the past. Or that there was an episode of delta formation that was much older than the current deposit that we see. So it could be very interesting for us to visit one of these remnants and potentially have an opportunity to study either a more extensive outcrop and more distal into the basin than the main delta, or an older episode of a fluvial deltaic deposition. So we'll, depending on where we land, we may end up being able to explore one of these remnants, and that can tell us, can add to our understanding of the deltaic processes that happened here in Jezero. And then finally, we have the marginal deposits, and I talked a bit about these before, because these are the ones that have the really strong carbonate signature. And so we think of these as possible shoreline carbonate deposits of great interest for astrobiology, and because of the presence of carbon for paleoclimate and understanding the carbon cycle on Mars when we get those samples back to Earth. And so the example I show here for our kind of best case scenario Earth analog, this is a site in Nevada called Walker Lake. And we actually ran a field test with our rover team here at Walker Lake. And this is a shallow lake margin that has just some fantastic microbial structures, and you can see some of those in the bottom panels. And so it would be just the best case scenario, ultimate discovery for us to find something microbial in the shallow margin deposits of ancient Lake Jezero. So this would be our dream, I think, of what we would hope to find at Jezero. And then finally, we have the crater wall. And this is particularly exciting as we think about some of the big questions on Mars about the timing and the age of some of these big impact events on Mars. And so present in the walls of Jezero crater are these what we call megabreccia deposits. So these are like house-sized and larger blocks. And it's possible that these blocks formed during the Jezero impact, but there's also evidence elsewhere around Jezero that there are these megabreccia deposits that could be associated with the Isidis impact event. And so these blocks could represent pre-Isidis ancient Mars crust. And so these would be truly some of the most ancient rocks on Mars, and we would have the ability to visit them and study them with perseverance and potentially sample them. And so these rocks could tell us about a period of Mars history that we otherwise couldn't access, or we wouldn't learn about in the other deposits, but this is what gives us the window into earliest Mars history. And these are big enough rocks that we could get geologic context from them, and we could understand what environments and settings they were deposited in, or what process formed them. So this is really exciting from an age dating perspective, to age date the Isidis impact and rocks that came before, and to understand what the pre-Isidis ancient early Noachian was like on Mars. Okay, so that's our tour of Jezero. And in my remaining time, I just wanted to tell you a little bit about what the science team is up to. We're not on Mars yet, but we are working very hard to prepare for our exploration of Jezero. And so the science team did a kind of internal crowdsourcing mapping effort to put together a geologic map of the deposits in Jezero so we could better understand what's present in the crater and to start building and developing hypotheses for what the rover could test on the ground and with an eye towards sample return and what samples we'd be interested in collecting. So we split up this area of Jezero into a bunch of quadrangles and assigned our team members each a quadrangle to map. And this was the result, which is the most detailed geologic map yet created for Jezero. And this was an effort that I led, and so I'm really proud of it, which is why I'm showing it to you. But this is really exciting to me in that we can use this map as a reference product as the rover is traversing in Jezero, so that we can constantly be updating our idea and the geologic model that we have for Jezero and what these deposits represent and what their relative ages are, because we won't get those absolute ages until the samples come back. But this is the start of us building that geologic context and acquiring the field notes for those samples that we hope to bring back to Earth. And then we're also using that geologic map to develop a notional mission scenario for Jezero Crater. And this was something the team put together around the time of the landing site selection process. And we are working right now to update this scenario. But we're thinking about what would our mission in Jezero with Perseverance really look like? Where would we go? Where are the highest priority locations we want to send the rover? And so these were two scenarios we put together. Of course, we don't know where we're going to land, but we can guess and we can put a plan together, knowing that of course that plan is going to change when we get on the surface. But we proposed two options. One that has us landing a little bit closer to the delta, and the landing ellipse has now shifted to the west, and so we now have about half of the ellipse is composed of the delta. So there's about a 50% chance that we're going to land just off the delta. And if you can see my mouse, it's probably this area, which is the smoother area, and avoid some of that really rocky terrain further out to the east. But if we land closer to the delta, we're in a great position to head right to the delta after we take a look at some of those olivine and carbonate bearing deposits where we have optimistically chosen to land in this scenario. But we would go check out that Mayfitt crater floor and then head to the delta, look at the delta's base where we think those distal delta deposits with a high potential for having concentrations of organic matter may be present, then up onto the surface to visit the diverse river deposits, and then back to the lake margin and looking at those carbonate deposits before we head to the rim to sample and study those that pre-Jezero and possibly pre-Isidis bedrock. Another mission scenario has us starting at the delta remnants, which I mentioned were interesting because they may give us a window into even earlier lake and delta activity in Jezero. We go and explore there and then make our way to the delta. In that scenario, it's a little harder for us to reach the crater rim in the prime mission, but on the other hand, we get the opportunity to examine those delta remnants, which are certainly an exciting potential target. And so this is what a notional sample cache could look like for a Jezero mission. And what is so exciting to us about this is that we think that this is the kind of sample cache that is diverse enough and has samples with compelling potential for ancient biosignatures to really advance Mars science forward and feed what may be generations and decades worth of Mars science. And so Perseverance has the ability to collect 43 sample tubes, 6 of which are witness blanks. But we have in mind the ability to collect about 30 or so samples for scientific samples. And so these would be the ones that we would look to collect in Jezero, and this is about 20, thinking that we could have up to 10 other sample tubes for further exploration and further sampling. But a cache like this would have potential volcanic rocks, a number of different sedimentary deposits with potential for ancient life to be held within them, as well as those most ancient rocks in the crater rim. And so we think that kind of a sample cache would really help us address this wide range of really compelling scientific questions. First and foremost, was Mars inhabited, and then learning more about prebiotic environments, and then the formation and differentiation of rocky planets, and of course, getting at that crater chronology and the geochronology aspect that would help us build that geologic timescale for Mars. And so I'll end here. This is, I think, amongst my last slides. And so wanted to put this out there because If our mission in Jezero goes well during the prime mission, and if the rover is healthy and still able to carry on, we would look beyond Jezero. And the area right outside of Jezero is Northeast Syrtis, and that was one of the compelling landing site candidates that was up against Jezero during the site selection. And so we have the potential, if the rover is ready to go, to move beyond Jezero and go explore that most ancient crust on Mars. And it's also a really exciting opportunity to go from, in this case, sink to source. But these rocks out here in Northeast Syrtis would be the rocks that sourced the deposits that are now found in the Jezero Delta. And so we're really excited about that potential, and it's something that we'll consider as we get to the end of the prime mission with Perseverance. And so I'll just put this up at the end and hopefully have time for a couple of questions. But Perseverance is the first step of a notional 3-mission Mars sample return campaign, which is currently in work at NASA with its international partners, including ESA. And so we look forward to the future and potential follow-on missions that would help get those samples back to Earth. And so I'll end it there and just say we're really excited to get to work on Mars with Perseverance, and really looking forward to tomorrow's launch and then landing in February of 2021.
Thank you, Dr. Stack Morgan. That was an awesome talk. And I think everyone's had a bunch of questions that shows they're really excited what you're doing. So we'll jump right into it. The first question is, from observations of the Martian surface, we have been able to see evidence for water on Mars, and we know that the water is a critical component for life. However, as you've said, that is not what we see today. What do we know about how Mars got and lost its water?
Yeah, that's a great question. And I think that's also one of the questions, the evolutionary questions that we're looking to learn more about with sample return on Mars. And I think this is the water history of Mars is a great example of the interconnectedness of the different parts of the Mars system. And we think about, in order for water to be stable on the Martian surface, you have to have atmospheric conditions that are suitable for the preservation or for the existence of liquid water at the surface. And so I think this is where you start to get into the ideas out there that Mars once had a magnetic field and it once had a much thicker atmosphere. But because Mars is a smaller planet and it's cooled a lot faster than Earth, for example, it lost its magnetic field at one point, leaving its atmosphere open to being degraded and blown away by cosmic rays, solar wind, that kind of thing. And so once you start losing the atmosphere, then you put the stability of liquid water on the surface at risk. And so that everything here has a feedback. And so from a planetary evolution perspective, Mars is such an interesting laboratory to study some of those big planet-wide processes that can really have an effect on a planet's habitability.
Great, thank you. So the next question is, one of the groundbreaking aspects about the Mars 2020 mission you've told us about is the preparation for returning samples to Earth. How will scientists decide which samples to return later? And is it an automated selection process?
Yes, so there are a couple of different steps of this decision-making process. The first one that we on the Perseverance team are most concerned with at the moment is what to put in that sample cache. And I've given you a sense of what we're thinking about there. When we're on the surface, we will have that plan in mind, because one thing we're interested in is the diversity of the samples, but we will be exploration driven just as other missions have been as well. But I think actually having a notional plan in mind will really help drive the mission forward. It's very easy for us to get bogged down at any one outcrop and think, oh, well, you could take 10 samples here that would be interesting and compelling. And so having this plan really helps move us forward and remember that there is more goodness ahead. So that's the first decision. How decisions would be made about which samples to return is more of a question mark. I think it depends on the caching, the depot strategy that we end up doing, and also the health of the rover. We have this ambitious goal that if the rover is healthy and well, we could continue on outside of Jezero. So we would think about, likely in that scenario, putting a cache down in Jezero, but perhaps saving some of the best samples for a second depot outside of Jezero. And so in that case, we would be very driven by the strategic outline of the mission. But the follow-on missions we are supportive of them being able to bring back the number of samples that is scientifically important and compelling, and that's something around 30 samples. But we'll have to make decisions about how those samples get apportioned on the surface of Mars and what's in a depot that could be reachable by a follow-on mission as Perseverance's mission unfolds.
Great, thank you. I think we have time for one more question here before we go. So why don't we go to this question? What can you tell us about the process the team goes through on down selection of the mission goals, objectives, and analytic tools? How do you make those hard decisions given the limited budget and other constraints for a Mars mission?
Yeah, that's a great question and would take a much longer answer than I probably have time to give. But I will say that the mission objectives are something that are defined pretty early on in the process by NASA and by a team that works to define what the science objectives of the mission should be. And that's done before the rover gets built. It's when the mission is in the concept phase. Same as well with the instruments, which can be interesting because the instruments are selected by NASA before you know what the landing site is. And so the science objectives and the instruments get selected very early on, and then later on comes the landing site selection. And so in this case, when we were thinking about landing sites, you do want to think about what your in situ capabilities are and which site gives you the best chance of making exciting discoveries with the payload you have. So those are things that for us on Perseverance, we didn't have a whole lot of control over. The decisions that we do have control over are where we go on the surface, what samples we put in the cache, and where we put those samples. And so those will come as a result of likely a lot of vigorous, energetic discussion on the part of the science team. That's how these decisions often go on a rover team. And so we have a team of over 350 scientists who I can guarantee will be very heavily engaged in talking through all of those decisions. But at the end of the day, you do have to come to a consensus decision, and not everyone is happy, but we do have in the future the promise of a follow-on mission. So we can't get too bogged down with those decisions, and sometimes you just have to go with it.
I want to thank you one more time, Dr. Stack Morgan. The talk was really fantastic. I know we're all looking forward to the launch tomorrow. I want to thank everyone in the audience for tuning in with us tonight. And also I want to put out a note that our next lecture will be on August 10th with Dr. Bethany Ellman, and she will be discussing the Lunar Trailblazer. Thank you all for tuning in.
Thank you.